We're still looking at our study of section 1.7, and we're specifically going to talk about how to add, subtract, multiply, and divide functions. Recall our functional notation. F of x is equal to y. Remember, this is not f times x, but f of x. This notation replaces the variable y. In example 1, we're given that f of x is equal to x squared minus 1, a quadratic function, and g of x equals 2x minus 3, a linear function. In A, we're asked to find f plus g of x. This notation may be a bit confusing to you. Remember, this is not f plus g times x, but function f plus function g. In example B, f minus g of x is f of x minus function g of x. In example C, f times g of x is function f of x multiplied by function g of x. And in example D, f divided by g of x is function f of x divided by function g of x. So we're going to go through these operations. I think you'll find this is very simple. In A, we'll take function f of x, x squared minus 1, and we'll add g of x to it, 2x minus 3. And you see that this is a simple problem. Always use order of operations. Remember parentheses, exponents, then multiplication and division, moving from left to right, and addition and subtraction, moving from left to right. So here we only have the addition and subtraction. I'll start with x squared, and as I look through the entire polynomial function, there is not another like term for x squared, so we'll bring that down. Negative 1 has a like term of minus 3. Negative 1 minus 3 is negative 4. And then 2x does not have a like term. So we're adding the like terms. In B, we'll take function f of x, x squared minus 1, and we will subtract g of x. Now, I want to point out something here. If I write the difference without putting a parentheses after 2x minus 3, then I would only subtract 2x. But the notation says to subtract the entire function g of x. So I will follow the minus with parentheses so I remember to subtract the entire function. That was not necessary in A because adding a number does not change the sign. Subtracting a value does. So we have x squared minus 1. We distribute our minus, or our negative, so minus 2x, and minus a negative makes that plus 3. So we'll look for those like terms. X squared does not have a like term. Negative 1 plus 3 is positive 2, and negative 2x does not have a like term. So far, we have added 2 functions and subtracted 2 functions. In example C, we will multiply those functions. So x squared minus 1 times 2x minus 3. We have a pair of binomials here, and you may recall that when we multiply binomials, we use FOIL. Remember, FOIL represents the first function times the first function, the outside function times the outside function, the inside times the inside, and the last times the last. And looking back through, I have an x cubed, an x squared, x to the first, and 3, a constant, so there are no like terms. Finally, with D, we will divide our f of x function, x squared minus 1, divided by 2x minus 3. x squared minus 1 and 2x minus 3 are not like factors. I could try to factor the numerator, and I'll do that real quick. Just note to myself, x minus 1 times x plus 1. There is not an x minus 1 factor in the denominator. There is not an x plus 1 factor in the denominator. So this function will not reduce any. So we've added, subtracted, multiplied, and divided a pair of functions. And let's now go back and find the domain of each combination, meaning the domain of the sum, the difference, the product, and the quotient. If I look back at A, so 2A corresponds to 1A. Remember that when we're looking for the domain of the function, we're asking ourselves, is there anywhere that would cause this function to be undefined on a set of real numbers? Remember, the function's undefined if we divide by 0 or if we have a negative under a radical. Well, there are no radicals in this polynomial, and there is not a variable in the denominator, so it's impossible to divide by 0. So recall that our domain is all reals. In example B, there is no variable in the denominator. There is no variable under the radical. So again, our domain is all reals. In example C, there is no variable in the denominator, nor is there a variable under the radical. So again, all reals. In D, there is a variable in the denominator. So recall, to prevent dividing by 0, we set our denominator equal to 0. So we're finding what number makes this denominator equal 0. To solve for x, we would begin by adding 3 to both sides and then dividing by 2. So if we were to plug 3/2 back into this equation, just to show you briefly, that would give us 2 times 3/2 minus 3. I know that 2 times 3/2, the 2's reduce, and 3 minus 3 is 0. So this number definitely gives me 0 in the denominator. So our domain is all reals. We do not want x to equal 3/2. So accept 3/2. Let's make an observation here. The sum, the difference, and the product all have the exact same domain. But the quotient's domain is different, and that's because there's a variable introduced into the denominator. So when you're finding the sum, the difference, the product, and the quotient of functions, the domains of the sum, the difference, and the product will always be the same as each other, but the domain of the quotient is the oddball out or the odd man out because it has a variable in the denominator.